right, so next one, I'm gonna introduce our next two machine learning tools, which is machine learning based fault detection and also seismic Facies segmentation. So these are the two application for detection by deep learning convolutional neural network, which C that stands for. And also for the Facies classification, or we call the seismic feature extraction, that also based on the convolutional neural network. So this is the salt floor that we built for our fault detection. We call the Paradise deep learning based fault detection salt floor, which include the 4 steps. So the first step is seismic data preconditioning. So when you got your seismic data, especially the pole stack, no matter is a depth migrate or time migrate, you may want to reject some random noise, or you want to enhance your seismic discontinuity in your seismic data. So that's how the seismic data preconditioning work. We apply a 3D structure-oriented filtering to enhance your seismic signal noise ratio and sharpen the discontinuity in the seismic data, which result in a better, more AI result. So AI is not the king, it cannot do anything. So if you can improve your input seismic data just a little bit, you may get a better AI result. And the second step is just to apply one of our pre-trained 3D scene-based fault detection module, or we call the engines in Paradise software. And engine is a pre-trained. So we trained our engine or model by many synthetic data volumes. We built more than 5,000 synthetic cubes that represent the seismic data and your faults, which has a different kind of deeping angle, azimuth, or orientation, and also your frequency band that for different volumes, and also the variation about the horizontal banding. So we want to get as many synthetic data to represent the different kind of faults that you may see on the different basin or your different data. So this step is just to select one volume and run with this model and get your result. And even the AI result showing a superior result than the conventional the edge detection attributes, such as coherence, variance that you may use for edge detection. So we still want to have the using an image processing based method we call the fault image enhancement. That using a 3D Laplacian of Gaussian filtering that enhance your AI result and sharpen your AI result. I will show some example with this before and after this third step. And with the enhanced imaging, and then we will run a structured tensor and calculate the orientation of your fault anomalies in your 3D seismic data. So note that I want to mention a thing that we want to make our tool that can be used by the different kind of people in the different majors, like geoscientist, engineer, maybe geologist. So Paradise Deep Learning Fault Detection Software is a fully automatic workflow. So once you get your 3D seismic data, you just need to input that and input your data to the Paradise software and build this software, and then it will automatically output the 3 volumes at the end of the last step. So the first volume is we call the seeing fault probability, which represent where the fault located in your 3D seismic data. And the other 2 attributes, which is very useful for your structural modeling, which is fault deep magnitude and fault deep azimuth. So the deep magnitude indicate the deeping angle of your fault in your 3D volume, which is a plano anomalies in your 3D volume. And the fault deep azimuth indicate the angle of the orientation, which is your fault deeping around in the 3D volumes. So with these 2 and 3, actually 3 and fault probability, with these 3 attributes, you can easily modeling your fault in your other, maybe in the Paradise or other commercial package. So let's quickly see some training cubes. Since we are using convolutional neural network, which is a supervised machine learning, or we call the deep learning. So we need some training data to train this AI and make this AI be sensitive to only faults because we are doing the fault detection. So this is our training data we generated. So for example, on the left column, this is the seismic amplitude data that we simulated based on the different frequency band. Here it's showing the reflector parameter we generated using for generate those seismic data. Reflector density indicate how your layer of coherent events, the density for that and in the different cubes or different training data. Reflector noise is the noise between the reflector, and the white noise, a Gaussian background noise that you may need in adding to the cubes. And the frequency, like a vertical shearing variation, that a dipping band, that we just want to make it a variable from compared to the different cubes. On the right column, it's showing the fault labels. So we're using these fault labels to shift this seismic amplitude to create the corresponding discontinuity in the seismic data. So that means that our label is 100% accuracy because they are all the synthetic data, 3D synthetic cubes. We use this label to create the seismic data and make that our training data 100% accuracy. Compared to the manual interpretation, so we may got the best training data for just the training data to train AI. And here are these some fault parameter. So every parameter that can random select to generate those fault plan in the 3D cubes. And here is everything that I show here. You may understand the deep azimuth, location, displacement, fault drag. That's something like here. So you may see some seismic amplitude data. If we have a discontinuity, it sees some maybe amplitude drag over here. So that's we also need to simulate to have some difference features in the cubes. And for number curvature, that means we want to simulate a straight fault or curved fault. So we want to try to generate as many as these different kind of fault. So for deep magnitude and azimuth, here I show here, this is a fault plan and how I define this deep magnitude. So the deep magnitude is the angle between this normal vector for the fault and the normal down vector. So this is the angle theta. Here is showing the deep magnitude. So that means that if we have a vertical fault, that means we have a 90-degree for deep magnitude. And if we have a horizontal fault, like a horizon, that means the fault deep magnitude is 0. So you may want to using this deep magnitude to threshold your fault between the different dipping angle, like steer plotting, and using the deep magnitude to maybe segment or classify your fault with a different dipping angle. And azimuth, as you can see here, azimuth, we use a cyclical color bar, 180, 0 in the middle, and goes back to minus 180. So this means that on the 0, we define that which is a fault oriented to the north for the Earth. And also the source is 180 degree. So we keep the cyclical color bar, as you can see here, make it a fault that's easily to be interpreted on even the 2D slice, or the vertical slice, or the time slice. And note that on here, I want to use here. So pointer. So here on the seismic data, here is the 2 major fault we labeled, and this is synthetic data. So it's 100% accuracy for the label. So most of the interpreter, there may be just pick these 2 major fault. However, there are only other 2 small fault over here. One is over here, other one at the top. So if you want to generate your own data, maybe with manual labels, you may miss these 2, which cause some inaccurate classification for your AI. But with the synthetic data, we will address every discontinuity for the training data and make our AI to be sensitive to the fault. Okay. So next, this slide is used to introduce our fault image enhancement and scalation. So imagine this 𝗟𝗲𝗿 rock as a fault plan on the 3D seismic data. So we can't examine all the discontinuity in the 3D seismic data if you have very large data. So we need to think about the automatic way to check the fault deep magnitude and deep azimuth. So here, we want to using a 3D, the method we call the 3D structured tensor that build on your 3D seismic data. So with the structured tensor, we can compute the second moment tensor from the different orientation we call that by decompose that tensor into the different perpendicular or this we call the vectors. So by decompose that the structured tensor, we got this 3 vector, V1 here. Oops, sorry. V1 over here, which is the normal vector, and the other V2 is also normal vector. So in the 3D data, so the V1 and the V2 represent your fault plane in your 3D seismic data. And V3 is just the vector perpendicular to your fault plane. If we got this orientation for a fault, then we can apply a 3D Laplacian of Gaussian filtering to enhance a fault plane that's through the V1 and V3 on this plane. And skeletonize this fault if you have very sick fault or false positive in your result. And we can skeletonize the fault along this V3. And these 2 images showing the example that if you only have an edge detection fault result, like here, a very bad resolution, and only apply this fault enhancement, you are getting a very good result. So let's see an example that apply the Paradise deep learning based fault detection software to a canyon basin in Australia, which is showing the shallow polygonal fault system. So on this data set, we have a 2 fault system. Actually. First is this white dash line, a shallow one, around the 2.3 second. This is a polygonal fault system. And also we have a deeper one over here, this white dash line. It's showing the major fault. So first, let's see the result about the first step seismic data preconditioning. So this image is showing the corresponding reject the seismic noise just by apply the seismic data preconditioning. So this is the original seismic data, amplitude data. This is the rejected noise from that seismic data. So note that the blue arrows on this image is showing the incoherent noise along those fault, along those major fault. So if we focus on here, and the red arrow at the shallow area indicate the coherent noise on this data set. They are the acquisition footprint, which is caused this strong amplitude data. You may see some like a coherent amplitude has also been rejected. That partially of them are the multiples, partially of them are just the coherent amplitude. Compare this level to the original seismic data. So the rejective noise level is very low. So that doesn't hurt our result for fault detection. So this is the seismic data after preconditioning. So which is the original seismic amplitude data minus this one, we got this filter data. And when we input this filter data to one of our pre-trained engine to calculate the fault probability, which is showing on this vertical slice. So note that the black color bar here is showing the fault probabilities. And this data is from the 0 to 6 seconds, which is time migrate data. And there are a lot of fault. And the AI almost help us to get all the discontinuity on these seismic sections. And especially this polygonal fault system at the shallow white dash line, and also the major fault here, some is cross fault. So the result looks pretty good. I see this fault trend that looks good, and this one is also very good, especially this one. And that makes sense based on my interpretation. However, we still see some false positive over here. So some might small discontinuity, some may just a false positive. I want to just reject that using our fault image enhancement. So the next slide is just a fault image enhanced result, fault detection result. So note that with fault image enhancement, we make our faults, which is here, more continuous and much sharper. And some false positive, or we call the noise over here, that caused by the AI has been smoothed and rejected, especially here. So with the fault image enhancement, we got a better fault result. And then we want to using this better one to calculate the fault attributes. So first is fault azimuths. Seeing here, the yellow color, cyan color, blue color, which based on this our color bar that indicates how the fault is oriented in your 3D volumes. So even on this vertical slice, we can see this fault, which has an orientation about -10 degrees, which means that for the north, it's just a -10 degrees to the north. So vertical slice just tell us that how the fault oriented and without examining the whole 3D volumes. If we want to see the fault orientation, you may just need to check the time slice by time slice. But right now with the fault azimuth attributes, we just need a vertical slice and see what the color it is. Same thing for deep magnitude. You don't have to generate your fault structural modeling in 3D. You just need the deep magnitude to see how this dipping angle changes on this vertical slice. This is the time slice result. The left one is showing the polygonal fault system over here. On the right is the major fault system. So note that the manual fault interpretation on this data set is impossible. And also, we can input our fault detection result after last step, get our fault probability, and input our probability into self-organizing map with your attributes to generate a stratigraphic result and your fault result. So this, let me just quickly show that. So I calculate the 9 instantaneous attributes. And also I calculate my fault probability using the Paradise AI fault detection software. I input all of those attributes together into a one sum self-organizing the 2D neural map. And we project those attributes into this neural map, and which is showing on this slice. So with the instantaneous attributes and the fault probability result, we are able to check all our how the stratigraphic change, and also highlight those faults along those stratigraphic changes. On the right is the seismic data, the corresponding seismic data. On the left is our sum result. Note that I'm using 8x8 neurons, which is we have 64 total neurons, and all our fault neurons located in this neuron 1. And this is the other example that my colleague Carrie and I work on this one and generate the stratigraphic result with a fault result that is showing on the here. So note that we make our fault neuron to be black, make it easy to see. And also preserve all our stratigraphic result as these colorful neurons. So the lower one is the one without our seeing fault probability. Upper one is the sum with our seeing fault. So if you think that synthetic training data maybe not the best for every basin that you see on the maybe industry or the different area. So you want to add your own labels as the input to refine your AI model. So there is a way that we can retrain our CN and make our CN to be specific to your data set. So if you get your data set that's showing some fault that our AI tool cannot detect, you can generate your label on Paradise software and input your label to refine our CN module. So this is showing how it works. Very easy. You just need to using our Paradise 3D viewer and open our polygon and polyline tools to draw some polygons on your seismic data and input your polygon to retrain our CN and make it work. So the only difference is on here, train or refine a CN module with a select polygon, which you generate on your 3D seismic data. Let me quickly show here. So this is some example about the refinement step. So with your seismic data, you generate your labels, and with those one, input to refine the CN. So let me quickly show an example that with my interpretation, not only the synthetic, but also my interpretation. So application to the F3 data set. So this is the F3 data set. This is the one of our pre-trained seeing engines. We calculate this pre-trained engine with our, we train this with our synthetic data. So it highlights almost all the discontinuity over here, especially this no parallel normal fault, some low angle fault, maybe pinch out here, some other anomalies, and also this gas chimney also cause a major fault. So this is my label, which means that I'm only interested on here, this normal fault and this major normal fault. I'm not interested on these small discontinuities and this pinch out, low angle discontinuity, and how here the discontinuity. I only am interested on here. I want to make my CN to be only sensitive to my labeled features. So this is how it changed. So I input my label to refine my CN. So this is just the refined CN at the beginning. It approx 10, which means that after 10 iteration training, and cost my 2 minutes. I got this one. Looks very similar to my original 2D printing result, yeah? After 5 minutes, I use very aggressive parameter. I want to just make my CN to be sensitive to my feature. So after approx 15, cost my 5 minutes. I got this one. Very similar, it's beginning similar to my labels. It's just to focus on this normal fault and make it better for this gas chimney and remove all other discontinuity which are not labeled on. After 120 approx, which cost my 20 minutes, I got this one, which is almost like my labels. So that means my CN has been refined and only be sensitive to this fault and this fault. Okay, so next is seismic Facies classification, also by the deep learning convolutional neural network. Similar to the fault detection, it's also like using the AI help us to recognize or extract the labels from your seismic data. So very similar to the fault labels and fault detection, but this seeing Facies one is for multi-class segmentation. For fault detection, it's just a binary classification, either fault or non-fault. But for Facies, we may have multiple Facies or multiple features in your seismic data. For example, you have a sand shell package, you have salt dome, and you have other maybe like a different package. So which means that you may need to draw polygons on your 3D seismic data and label those features like this red green and this blue. And then let the AI know that this is my feature. Help me to extract all features from other inlines. So this is just, you only need to pick maybe 5% to 10% of the data, which means that if you have 100 inline, you just need to pick 5 inline and input AI and let AI to help you to segment all your Facies from other 95 inlines. So we're using the convolutional neural network model, which is here. This is the Deep Labs 𝗟𝗲𝗿𝗂𝗂 model developed by Google. A very good one for image processing. And input your seismic amplitude data with your label that you draw a polygon, our software. And then let AI do the training and then do some validation, find the best model that give you that. And then you just need input your whole volume into this pre-trained model and getting the final result. So let's quickly show an example, still the F3, but here I just labeled the Facies, not a fault. If you remember, for the fault example, I just picked here and here. But for Facies, I don't want a fault. Fault is just my background. I want every feature that I'm interested in here. For example, this shallow layer, and here is maybe some stratigraphic changes like turbidite, and here is some bottom like a carbonate, and this one is a salt dome. I'm interested on these Facies. How many? Totally 8. I labeled. Including the background, there are 9 fishes. So train the AI, so this is a prediction of the AI that on the same inland. So I input this one into AI and let the AI works training, and then give me best modulars. I apply this volume to the modular and getting this result. So compare these two, you will see that it's almost the same compared to the training line. So this is a validation result on the same inland. This is my label. This is the one AI gave me on this inland. So how about the test inland? So that means that on this inland, I have nothing labels on here for training. So this is just a test line. And this is my test line result. Seismic data, AI prediction fishes. If we go back to my training inland, so this one, this color means my labels. This is a prediction. So compared to the test line, which is inland 320, so you will see that all the shapes makes very good sense for my experience interpretation, and especially this salt dome. And all the colorful here, colorful features here indicate my interpretation on these labels. 8 is my salt, and the other is a carbonate, shale package, sand package. So here I only draw 5% data on inlands. How about the crossline result? Is that still good? So this is the crossline test crossline. So this colorful dash line indicate my labels on inland. But right now we check the crossline, which is perpendicular to inland. It's showing just like this dash line here. Green, cyan, yellow, orange, red over here. See the thickness over here. My label looks pretty good. And also the salt dome, I capture all the salt edges over here. And I draw a polygon here on the seismic data to show my prediction. So let's focus on these two parts. And this is my prediction, AI prediction on this crossline. Even I only do the training on inland, I still can get a very continuous result on crossline. So that means my AI is doing very good. So on the inland, both inland and crossline. So back to here, polygons. So this is my polygons, that my interpretation on crossline. And the colorful background, the classification, like this orange and green is the AI result. Note that the edges looks pretty good. Overall, I mean, yeah. How about the time slice? This is the same one, but on the time slice through the 1.484 second. And this is my label at this time slice. And this is the AI result. Know that here. I know that here, which I didn't pick. Especially the edges. Let's check the edges. There's the salt dome over here. Maybe you can see here, the pink dash line here, and see the result, just this small area through the time slice. So we can using these AI tools for for the feature segmentation or the feature extraction over here. And with this 5% supervised data, we can segment all the layer. And then once we got that, we can just run one sum on just one layers. If we have like a channel over here or turbidite, we are interested on the specific layer, we just run a sum on that. And with the sum, we can iterate to highlight those feature changes in this classification. So you don't need to run the sum if you don't have the horizons or other constraint in your seismic data. You can using these blocks and extract your seismic data and generate your corresponding attributes on this area and run a sum for that area. So this is one test result that's showing the turbidite, which we are interested in, with the sum, and also this deep learning AI tools. We can quickly define those turbidites this data set. And also the channels. This is the channel target in turbidite on the neurons. Okay, so with these two tools that both are the deep learning convolutional neural network model that can produce a very high quality. For fault detection, that means the fault probability. For fishes, that the high quality for fishes segmentation result. And for fault is a binary issue, so that means fault detection just classify the data into two classes, fault or others. But for fishes, you may have a multi-class segmentation result. And usually we think about the AI tool, we may need to spend more on training an AI, but actually, the actual application cost is very low right now. So that's based on the optimization of the software. And the neuron corresponding to the reservoir can be isolated in the 3D volumes. So this is just our deep learning-based fault detection and seismic fishes classification. And one more thing I want to mention that, so with the AI tools, even not you want to just run something like feature extraction, salt dome, channels, or others. It's just like an image. So we are not talking about the seismic data anymore. Even you have the seismic depth migrate data, you want to talk about the waveform, wavelength, and the wave number, or the seismic time migrate data. You want to talk about the frequency, time samples. But for the AI, we just talk about the imaging. And for the input, you can think about is everything for the seismic data is a gray level imaging. So that's how AI works. Thank you.